Great. And you all can see the lecture slide. So yeah, just a couple of announcements. As you know, homework 1 is due today by the end of the day. Homework 2 will come out right after class today. And originally I set the deadline to Feb 3rd, but since our lectures are a little bit off, a little bit later, so I've extended it a couple days to Feb 5. And it didn't apply to this Monday because there was a holiday, but next Monday and going forward, the office hours are moved to 1 to 2 p.m. Because there's a conflict with the room that we have the office hours in. So we needed to move it to avoid a different class. Yeah. Okay. So today we're going to continue on MPI, and if we finish, then we can move on to caching. So just to recap from last time, we were learning MPI, which is this programming language for message passing. It's mostly for it can be both for shared memory and distributed systems. And one nice thing about it is that if you write your MPI code, like you have this notion of a process, which in this picture is like, you just have a bunch of, you can think of it as like parallel workers, and each process is executing the program, like a copy of the program independently. And you don't have to worry about whether the process is like a thread or a core, like in shared memory, or a different node. Like in distributed memory, you have a bunch of machines connected by a network, and you don't, in MPI, you don't have to think about whether or not, like from a programming point of view, those can be nodes or cores, and it will just work, which is really nice because you don't have to rewrite your program if you want to move to multi-node. And the way that you can think about MPI is you have a bunch of parallel processes, P processes, and they have ranks 0, 1, 2, up to P minus 1. And when you write your program, every one of these processes is executing the code, just a copy of the code individually. And they may not execute it at the same rate. So this is an example, like the most basic hello world example that we were doing. This is how you get this is how you get 2 nodes and 4 tasks per node on the cluster. So that would be 8 total processes. And then you can run MPI hello world, and this is the output. So notice that the ranks are not in order, like here 0, 2, 3, 4, and so on. Because, like I said, the processes may not be executing at the same time, or they may not be executing in the order that the ranks are given. Sometimes in your program, you need to have synchronization, which is that you define a stopping point in your program that no processes can go beyond that point until all of them reach that point. And maybe that point is like they all needed to compute some partial results, and then you're going to collect them together. Or they all need to, or like maybe you need to get to some point so that all of them have the correct input for the next step of the program, and that's synchronization. And you can do that explicitly with something like MPI barrier. So that's this. And remember that the communicator is like the world that you're given with all the processes in it. So you just pass in the communicator to the barrier, and that will tell all the processes that they cannot pass this point until all of them have reached that point. You can also do implicit synchronization yourself through send and receive, which we will talk about in a minute. And one way to determine whether you need barrier is to ask, like, if you have 2 processes and one of them was much faster, like 100 times faster than the second process, would your results still be correct? Yeah. So this is an example of how you would use barrier. You probably actually, you might need to do this sometimes to like debug, but one way to do it is like, so previously in the hello world, we didn't have any guarantee about which order the ranks would print in, but with this one, we iterate over the world size. So every process is going to execute this code. So there's for loop, which goes from 0 up to the world size, which is the total number of ranks. And there's a barrier inside this for loop. So all the processes have to reach this point until, and then you can continue. And the way this works is that if I, which is the for loop, is equal to the world rank, which is the current rank of some processor, then only that processor will print. And then you come back around and everybody will wait again. So this is the synchronization. And this is just printing if so we're going up the ranks 1 by 1, and this would only print if we're on the current rank. And so this is like the copy of the program that every process is going to run, and the output is now in order. So rank 0, 1, 2, 3, up to 7. So there's P equals 8 in this case. So P minus 1 is 7, and it prints 0 through 7. But it's important not to use barrier unless you need it because it does cost something. So all the processes may have to wait. But it might help like in debugging, like then you can order the output and it's probably easier to read it that way. Okay, so the most basic part that is the foundation of everything in MPI is called send and receive, because MPI is based on message passing. And with two processes, send and receive is just like this. Some process, like in this example, process 0, has some data that it wants to send, process 1. And so if one process is sending data, there needs to be matching a call to receive. And they both should ideally match the data as well. Like the data that process 0 wants to send to process 1 should end up on process 1 in its entirety. So things that need to be specified to get that to happen. One is how is data described? So for example, like what type of data or how much of data, and how are the processes identified? They need to be identified by rank to tell who is participating in the send and receive. How is the receiver recognizing and screening the messages? So like, how do you know this is the correct data that was meant to be sent? And what does it mean for send and receive to be finished? So to describe what data is, you can think of it as an envelope that has two parts. The data is inside of it, and it has things like the start of the message buffer. So it's like a pointer, and the counter of how many elements are going to be in the buffer and the data type. So for example, you could say like, I'm going to send 10 ints and they're starting at this pointer. And an envelope is the outer part, which tells you which source and destination are involved in the send and receive, a tag, which is like a unique identifier that you can use, and the communicator, which is the total world that all the processes are living in. The data in message for send and receive, yeah. So the data, you can describe it as a triple, which is a pointer, an address, a count, and a data type. And a data type can be recursively defined as, so there's some base data types in MPI, like MPI int and MPI double. And the simplest way is just, if you're just like, for example, sending an array of ints, you would say, I'm going to send however many count of int type. But you can also recursively define data types using these basic types, kind of like how you define structs in C or C++. So you could, yeah, you can make like a block of data types, you can make an array, you can make an arbitrary struct of these types. Most of the time in this class, I think you just need to use the basic types, like just an array of MPI int or double or something. But you can make more complex ones. Okay. So, like I said, the most basic pair of commands in MPI is send and receive. And these are the arguments to send, which is a void pointer to some buffer. So that's a pointer to where the elements are. A count, which is how many you're going to send. A data type, which is like an int or double. A destination, so this is a rank. So the destination rank that you're going to send the data to. A tag, which is an identifier, and the communicator. So the communicator, in the beginning, you can get a communicator from MPI that's just given, which is every process. And later on, we're going to learn how to make like sub communicators. Sometimes you may be interested in like splitting the world in half or something like that. But in the beginning, all the processes are the communicator, and this is just like the metadata about the world. So this basic send, this is MPI send, is a blocking send function, which means that it stops the program when you reach send, and it won't continue until the send has completed. And for this definition, completed means that the data has been delivered to the receiving system, and then the buffer, so this void pointer buffer, it can be reused. And it may not have been received by the destination process because there's still like some layers of the networking stack that needs to go up, but it just means that this buffer on the sending side can be reused. And then the corresponding one is MPI receive. So it kind of looks similar. There's again this void pointer to buffer, which is now where you're going to fill in the data, how many you're going to receive, which is count, the data type, source, which is just the inverse of dest, tag, communicator, and the only extra thing is status. And status, we'll talk about it in a little bit, but you can query some information about status, like how many you actually got, stuff like that. Yeah, so you can define the source, like in the basic example, if 0 is sending to 1, then the source would be 0 and the dest would be 1. You can pass in MPI any source or MPI any tag, and message tag is just like an int. So if you don't care about it, then you can just pass in any tag. And you can receive fewer than count. Like, for example, if count is like 100, you can receive like 50, and that would be fine, but receiving more is wrong. And you can get how many you actually got by querying status. So this is how you send and receive. So status is like something that you fill in. It's a struct that MPI provides. This is the initialization. You get your rank by using MPI com rank here. And here, just assume that there's two processes participating in the send and receive. So for the send, so process 0 is going to be the sender. And it fills this buff, which is like an int with just a random number, 1, 2, 3, 4, 5, 6. And it calls send. So it gives the pointer to this buffer. The destination is 1. Int, this is the tag. Yeah, tag. Oh, source tag communicator. Okay, so this is the number, the count, and then the source, or sorry, the dest in send, the tag, and com world. And here the count is 1, the source is 0, the tag is 0, com world, and status. And notice that both of them used buff, but it was because MPI is running a copy of each of these things, like buff is separate on rank 0 and 1. So the sender has filled it in here, but the receiver hasn't filled it in. So it's going to get it into this int. And at the end, both of them will have 1, 2, 3, 4, 5, 6. Well, actually, it's not defined what is in buff after the sender does send it, but rank 1 will have 1, 2, 3, 4, 5, 6 in buff. What's the tag? Okay, yeah. So the tag is, so I'm going to say it right now. The tag is just some user-defined integer tag that could help identify the messages. So one way that you might think about the tag is like if you want the sends to be ordered in some way, you can give the tags in that order, like 0, 1, 2, 3, and so on. If you're just sending one message between two processes via send and receive, doesn't really exactly matter what tag you use unless they as long as they match. But you can also pass in MPI any tag if you're just going to receive like one, or you don't care what order they come in. Did I answer the question? Yeah, so it's just like an identifier. Does MPI guarantee that buff stays defined? It copies all the data. So in distributed memory, the two processes may be different nodes. So there's no shared memory, there's no shared address space between them because they're different machines. So in distributed memory, you would in MPI, they would actually copy the data and send it to a different node through message passing, which under the hood uses like basic networking. So it'd have to go through like the entire networking stack to send the data. Yeah, and it can't send the pointer because if they're different nodes, they don't have shared address space. And can I repeat count? So count is just how many elements are going to be sent. So like example. So let's look at send. So the signature of send has a void pointer to the buffer, an int count, and a data type. Let's just look at the first three. So here, this is the pointer to the buffer. This is how many are going to be sent, which is 1. And this is the type of thing that is going to be sent, which is MPI int. So yeah, so in this case, we're sending 1 instance of int, but you can send as many as you want. You just pass it in there. Thank you. Yeah. So so that's send and receive. And those are, oh yeah, and finally there's status, which is like this last thing in receive. And status is just a struct that has some information about the message that was passed. So it contains like MPI source, which is the rank of the process that actually sent this message, tag, which is the tag, and error, which is an error code. And the reason that it has these metadata is because you can pass in any source and any tag in the source and tag parameters. And so like obviously there would actually be a discrete source and a discrete tag, but a receive can theoretically take in any source and any tag, and you would just get like anything that matches this description of count and data type. It doesn't really matter, like it doesn't really matter what buff is, because buff is like something on the side of the receiver. So yeah, so if you actually want the concrete source and tag, you can query status. Question, why is MPI status in receive and not in the MPI send function? Because you cannot pass in any, there's no any dest in send. You have to specify a specific destination to send to, but source can receive any from any destination. So like dest is well defined, and tag. I guess you can pass in any tag in send, but you can query it. Mostly it's in like in some sense send is like more well defined because receive is just like getting something from send. So yeah, so it may not have a source and a tag up front, but send defines the source and the tag, or send defines the dest and the tag. How can receive handle incomplete messages? So receive is allowed to handle a smaller count than the incomplete message. Or sorry, it is allowed to, so like let's say that you specified 100 as the count, you can receive any number of, let's say, ints less than 100. And by querying status, you can, status, I think. Hold on 1 second. Yeah. And in a second, I'll tell you how to query status to get how many you actually got. So maybe I can go on for like one slide and like you can tell me if that answers your question or not. So another way to query status is there's this function MPI get count, which passes in the status, the data type that you expect, and this int pointer to count, which count is going to get filled in by this get count. This is similar like how rank works and stuff. So in get count, you pass in status and the data type, and it returns out the count. It fills it in here. And count is the total number of data type elements that you actually got. So this is how you know the concrete number you actually got. And one reason that you might be interested in this is that if you don't exactly know upfront how many you will get, but you have an upper bound on how many you might get, so you allocate your memory to hold the max you might get, and you may get fewer. Thank you. Okay. Question? Are any other questions so far? Okay, so we can move on. So far we have done send and receive, and the most basic, oh, sorry, aren't the source and tag from MPI status redundant since they're already included? They are redundant if the destination or if the received message already had a concrete tag. Or sorry, so let me go back. So in MPI receive here, you can pass, there's some special MPI thing, like, you know, like some predefined MPI things, such as like MPI in. There's one called MPI any source and MPI any tag. And so the receiver could receive anything that matches the description of count and data type from any rank. And so in that case, you wouldn't have a concrete source and you would have to query status if you were interested in the rank that you actually got it from. So yeah, okay, so going back to this. So far, the most basic send and receive are blocking communication, which means that the process stops until it has finished either the send or receive, whichever one it's doing. And receive is not complete until the buffer is full, which means that like you passed in a pointer that you have to fill in with some message, and it's not going to move on until the buffer is full of stuff and safe to use. And send is also the inverse, which is it's not counted as finished until the buffer is empty or available for use. Exactly. It doesn't have to be empty. It just means that it's safe to write over that buffer. So you're not guaranteed to have any, you're not guaranteed what's going to be in there, but you're guaranteed that you are allowed to write over it because it has been successfully on its way to the receiver. And completion, yeah, completion depends. The time it takes will depend on the size of message and the amount of system buffering. So that's something lower level. This is a picture, like the sender sends some stuff, and then the receiver will receive it. And the sender has to transfer the data from the source buffer, and then that will complete. And the receiver receives it in the buffer, but then it has to, like, it receives it in a multi-node system, it receives it physically in the buffer, and then it has to make its way up the networking stack. So that would take some time. That's what this is. You have to be careful when you order your send and receives. So let's say we had this example. So you have two processes, process 0 and process 1. Process 0 wants to send some data to process 1, and process 1 wants to send some data to process 0. However, depending, like, let's say that both of these messages are pretty big, then there may not be sufficient storage at the destination to receive the data until it has cleared out the buffer of send 0. But then you would have the same issue on process 0 of receiving this data. And so there's a deadlock, which means that you have circular wait. So process 0 is waiting on some resources for process 1, but process 1 is waiting on some resources from process 0, in this case space, and so neither process can continue. And this is called unsafe because it depends on the availability of the system buffers to receive the data. In this case, your program would just halt because there's no, like, neither of them can clear the data until the buffers are cleared on the other end. Some ways that you can avoid it. In this example, you can order the operations more carefully. So here we match the send and the receive here. And here we can match the receive and the send. So this means that there will definitely be guaranteed to have this buffer because we're not trying to send the entire message at the same time to process 0. Another way is that there's this MPI called send receive, which we'll go through the function signature in a second, but you can think of both. You can think of it as both doing send and receive concurrently. So this is the function signature for send receive, and it looks like a lot, but it is basically just the parameters for send and the parameters for receive concatenated. So like for send, there's like a buffer, there's a count, and there's a data type. So those are the first three things. And then there's the recipient, which is the dest, the tag, and that's it for send. And then for receive, there's the buffer, the count, the data type, the sender, a tag, and because they're both sharing the communicator, so you only need one communicator, and the status is for the receive. And the buffers for the send and receive need to be different because you're not guaranteed that it's safe to write over the send buffer with the receive information. And this is an example. So let's say that we're only interested in 2 ranks, and the buffer that we want to send is, if my rank is 0, then I'm going to send 1, 2, 3, 4, 5. And if my rank is not 0, then I'm going to send 6, 7, 8, 9, 0. And here the tag is just 0, and the peer is just the other one that I'm not. So if I'm 0, my peer is 1. If I'm 1, my peer is 0. And both of them will call send receive. And both of them have a buffer send and a buffer receive, but these are different because you cannot assume that the 2 ranks share the same address space. So these are, even though they're called the same thing, they are different on each rank. So you have buffer send, buffer receive, and these are just like the things that you would get in send and receive. And at the end of this, they would just have flipped the numbers. So in the beginning, rank 0 had 1, 2, 3, 4, 5. In the end, it should have 6, 7, 8, 9, 0, and vice versa. So yeah, P0 sends 1, 2, 3, 4, 5, gets 6, 7, 8, 9, 0, and then P1 sends 6, 7, 8, 9, 0, and gets 1, 2, 3, 4, 5. Questions? So another way to do another way to avoid deadlock. So this one is probably more more popular maybe than send receive, and also people often use it to get better performance. So it's called non-blocking send receive, and that means that you send or you call the non-blocking send receive, which is called I send and I receive, and they both return immediately. It doesn't mean that the send and receive have completed, but it just means that the program can continue. And then it returns like request handles, which are things that you can query about whether they have completed. So basically the way it's going to work is that you call I send or I receive, you do some other stuff that your program may need to do, and then at the end you wait on whatever request and status were given, and only after the wait has completed, which means that the send or receive has finished, then the program continues. Yeah, and you cannot access the data buffer without the wait terminating successfully. So we will see some examples in a moment. So this is the function signature for isend. It's kind of similar to send, pretty much exactly the same, except now at the end, there's a request. So these are all the same, like buffer, count, data type. But at the end now, there's this request handle. And this is a handle on this particular operation, and you use that later to check whether the operation has completed. And you cannot reuse this buffer unless you have checked the request for completion and seen that it has been completed. Because you're not guaranteed that like you can write over this. And the way that you check for completion is through this MPI wait. So you get this request handle through isend. Like this is something that gets filled in. And then you call MPI when you're ready to check for completion, you call MPI wait, and that you can call yeah, so you passed in this request and it fills in the status. And it blocks until the whatever was requested, or it blocks until whatever is associated with this request handle is finished. And then test is just a non-blocking version of it. So you can test whether it's finished, but you cannot, it will not wait. So like you can imagine that wait is implemented with a while loop on top of test. But you can also test without blocking. And sometimes you may be interested in waiting on multiple requests, and there you would just have a count with how many requests, an array of them, and then array of status. Wait any means that if any of them in this array of requests finishes, then you continue. And wait some means that if the ones in this array of indices have completed, then you can continue. And then there's test for each of these. But probably most commonly you would use I send, I receive, and wait. So this is an example. We want to send this number 1, 2, 3, 4, 5. And this request is here. We're going to fill it in isend. And so we call isend. This is the send buffer. The count is, oops. The count is 1. The type is int. Destination is 1. Tag is 0. And com world and request. So this is a handle. And you can do other stuff, like not relating to this buffer, but you may have other work that the program needs to do. And then now we need, well, now this is the end. So we call wait, which we pass in the request handle, and we don't care about the status, so we pass in MPI status ignore. And this is blocking, and then we break out of this case. So that's the end of this center case. Oops, yeah, so this is, yeah, we're sending 1, 2, 3, 4, 5 using isend. And then in the receiving case, it doesn't have to be an I receive. It can be, but we can just also use a regular receive. Since this is the only thing in the receiver case, it's fine to just use receive. And this is the receive buffer. We're going to get 1 MPI int. The source is 0, tag is 0, com world, and we don't care about the status. And then we would receive 1, 2, 3, 4, 5. Questions on that part? How does MPI work if the machine's data types are not the same? I think MPI and MPI, like the MPI data types are fixed size irrespective of the machine data type size. Like as the MPI data type, you cannot pass in like the basic data types you see like int, long, stuff like that, you have to pass in like MPI int, MPI long, or MPI double, stuff like that. And those are well-defined sizes. Oh, but if, like, for example, if let's say an MPI long was 8 bytes, and then if you read it into a void pointer buffer that is that like is not long enough, is that the issue? I think maybe you should be careful to pre-allocate the buffer to be big enough. Like you could define the buffer here, we just defined it as int, but you could define it like as size of MPI int, something like that. Um, okay. And then there's this corresponding iReceive, which is the same as receive, buffer count, data type, sender, and then it just has this extra thing, which is request, and that is the handle. So we would check on it in a similar way to iSend. Then you would use wait, test, wait or test on this request. Yeah, so this is an example of using iReceive. This is the same. This is the same. Assume that the sender case is the same as we had before. It's just a different way to do the receive. That you can issue this iReceive, you pass in this buffer, and then you do some other stuff. Like here, it's just printing, but you could do whatever else needs to happen in the program. And then at the end, once everything else is completed, we can call wait, and that's going to block until this request is finished. And then at the end, we would get 1, 2, 3, 4, 5 into this buffer. And one reason that we also may be interested in using these non-blocking send and receive is, let's say we had this case where we have P processors and they all want to send in the cyclic way. So 0 wants to send to 1, 1 wants to send to 2, 2 wants to send to 3, so on like that. And then mod P at the end. If you just send and receive, it may block in the same way that we had deadlock before. But if we use the non-blocking receive, then we can avoid that because we can issue the non-blocking receive. Questions? So I'm going to talk very briefly about collectives, just because you might need to use one of them in the homework, but we're going to have an entire couple lectures on collectives later. At a high level, collective communication is a type of communication where all the processes have to participate in it, all processes in the communicator have to participate in it. And all collective operations are blocking, which means that the program cannot continue until the collective has finished. Without MPI barrier, you cannot assume that there is synchronization. And because they're blocking, collectives are guaranteed not to interfere with point-to-point messages. And they can be implemented using only point-to-point calls, which you will see in the next programming part. We're going to implement some of these using just send and receive. So these are some basic types of collectives. Broadcast. So broadcast is the most basic one. This is data, this is processes. So let's say we had 4 processes and we have some data on process 0, which is A0. And we want A0 to show up on all the other processes. So we would call broadcast, and now A0 shows up on process 0, 1, 2, 3. And then we have scatter and gather. So scatter and gather are inverses of each other. In scatter, process 0 has 4 data pieces, A0, A1, A2, A3. And then each one of these is going to end up on a different process. So A0 ends up on process 0, A1 ends up on process 1, A2 ends up on process 2, A3 ends up on process 3. And gather is just the inverse of that. So if we had this situation where everybody every process has some different piece of data and we want to put them all on A0, or sorry, on processor 0, then we call gather, and then we would end up in this situation here. And the one that you need to do in your homework is this reduction. So let's say we want to compute a sum over n elements. So we have a sum, and we want to accumulate some array elements into the sum. We did talk about algorithms, how to do it in parallel, but you don't have to implement them because MPI provides this reduce function. And the parameters are the source buff, the receiver buff, the count, data type, the operation that you're going to do the reduction on, the root, which is where the reduction should end up, and the communicator. So let's assume that every processor has one element that we want to reduce. So we put A, and we just have an array, which is indexed by the rank. We want to accumulate them all into sum. Let's say that the root, we want to accumulate the sum onto process 0. And so we call reduce. So A is the number that we're going to accumulate, is like the source number that we want to use in the accumulation, which is this A of 1 here. Sum, which is the end buffer where we want the end result to end up. 1, which is the count. So notice that the count is not number of ranks. The count is just how many things are we reducing per process. And the type is int. The operation is sum. Root, which is where we want the sum to end up, is 0. And com world is just the total communicator. So you can pass in something that's not 1 in the count. And that doesn't mean like you would sum up. If you pass in something that's not 1, or sorry, the thing that you pass into count is the number of elements that will end up on the root. So the way that the reduction works is that, like, let's say you passed in 2, then everybody would have 2, and you would kind of pass them, you would kind of sum them like column wise. So the first element that ends up on the root is the sum of all the elements in the first column. Second element on the root is the sum of all the elements in the second column. So it's not like you reduce 2 of them horizontally and then reduce them vertically. Yeah, so that's reduction. And yeah, so this is all that I want to say for the very introductory part to MPI. Is that MPI is the standard for programming distributed memory machines, but it can also be used in shared memory. And one nice thing is that the abstraction of process, it's opaque to the user whether it's a shared memory like thread or a distributed memory node. And if you move from shared memory to distributed memory, you don't have to rewrite your code in MPI, which is pretty good. And the core functionality is send and receive and variants, like we talked about on blocking send and receive. And you can build all the rest of the functionality on top of send and receive, like the collectives. Yeah. Any questions on that part? So we can move on. Mm, that's okay. So we're going to move on from MPI, but I will post the slides. And I think, yeah, I think reduction is pretty much all you need for homework 1. All right, so we're going to do caching, and I think the next couple lectures will be about caching and cache efficient algorithms. Okay, So we're going to talk about the memory hierarchy. And for now, we're going to do it on one processor. And one question might be like, this is a high performance computing class. Why would you be interested on the memory hierarchy on one processor when we've been talking about parallel processing? From a theoretical reason, the reason is that we don't have great models for the combination of cache hierarchy and parallelism. And also because it's hard to think about the combination of them. And it's still useful to think about them on one processor because it's sufficiently complex. So I said in the first lecture that memory limitations are a huge factor in overall performance. Most applications run at less than 10% of peak performance, and you can determine peak performance by, like when you buy a machine, it'll tell you, for example, it'll tell you some clock rate, like it runs at 3 gigahertz, for example. And if you have 8 cores, and each one has 3 gigahertz, then the total would be like 24 gigahertz in some theoretical peak of performance. But in reality, it is unlikely that you will do 24 gigahertz on this machine because of the memory hierarchy. And most of the performance is lost, like often, like something close to 10, like less than 10% is kind of even optimistic. Like sometimes things run at like 1 or 2% of peak performance because flops are really fast. And the reason that this performance is lost is because of data movement. So this plot is the relative performance over time, like how performance has improved. So starting from 1, which is normalized, everything is normalized to 1, and then going up to 100,000. And x-axis is year, and these dots are just different machines in the different years. You can see that processor speed has gone up over 10,000 times between the 80s and 2010. This kind of slowed since 2010. Then we got more multi-cores, but still. And then the memory speeds are increasing much more slowly, like probably less than 10 between the 80s and now. There's a gap of over 2,000 times. And so the takeaway from this is that if you're only optimizing for flops, it is unlikely that you will achieve up to here. And so why are we talking about serial performance in a course in high performance computing? Because like logically, the memory hierarchy, you could think of it on a single processor with one single worker. From a practical perspective, when you are trying to optimize code, starting with a fast serial implementation is an important first step towards a fast parallel implementation. If you start with a very slow serial implementation, even if you get perfect parallelism, it may not be as fast as a very optimized serial implementation, or even like a not so. It may be like similar in performance to a not so optimized serial implementation. And often serial implementations can access optimizations that parallel ones can't. So starting with a fast one is definitely important because that's like kind of your starting point. And if you parallelize slow serial code, then you will get slow parallel code because you can only get up to p speed up theoretically from parallelism. And so this is an example of somebody optimizing matrix multiply, and you're trying to decrease the runtime, so down is good. X-axis is just the size of the matrix. So the naive 3-loop version is this green thing that we have done before, just IJK, and it's getting much worse. And this red one is optimizing on one thread, probably using things like the memory hierarchy, because you don't get parallelism. And this is 131 times improvement, just using one core. And then if you have 8 threads, this is this pinkish thing, and you can get at most 8 times speed up on 8 threads. So this is a very dramatic example. Not all things will be as amenable to single-threaded optimizations like matrix multiplication, but you can often get something like 10x improvement just from sequential optimization. So first we'll do the basics of the memory hierarchy. There are a couple of costs to memory accesses to load and store. So these are similar to the costs that we have been talking about for message passing. The first is latency, which is the cost to load and store one word. So that is a fixed cost. Are those numbers for square? I think so. I think n is like this idling. So the latency is this fixed cost to load and store one word. That doesn't change no matter how many words you load or store. But the bandwidth is the average number of but the bandwidth does kind of, it's not dependent on how many bytes you're storing or loading, but you can only reach like the sustained maximum bandwidth if you're loading and storing many bytes with respect to bandwidth. So bandwidth is this average rate to load and store a large piece of data. So in your memory bus on your machine, it might tell you something like, oh, it's 2 gigabits per second, something like that, and that is bandwidth. But you probably will not achieve 2 gigabits per second if you're storing one word. You need to store many of them. And bandwidth is this throughput, which is bytes per second. Low bandwidth is like, bandwidth is not to do with the length, it just kind of has to do with the volume. So low bandwidth means you can only move a few things at a time. High bandwidth means you can move many things at a second. Latency is the delay travel time, which is fixed. And it doesn't depend on how many things you send, or sorry, doesn't depend on how many things you load or store. So low latency is like this example of this short hose, and then high latency is like longer. So it doesn't matter how much stuff is traveling through this. Yeah, so this is just an example, or this is some more data to illustrate why we would be interested in studying the memory hierarchy. So this y-axis is balance ratio, which means the flops per memory axis. And up is bad from the perspective of from the perspective of flops being useful, I guess. Like if flops are very fast with respect to memory, then that means it doesn't matter if you make the flops much faster because you're bottlenecked by the memory. So this is memory bandwidth, and this is the balance ratio. And you can see that the gap, like this thing going higher means that the gap between flops and memory bandwidth is growing. And it's growing about 2 times every 5 years or so. The x-axis is time. And then memory latency is even worse. So again, up is bad. Up is like how many flops can you do per unit of memory latency or memory bandwidth. And the red line is memory latency and is even higher, like almost 2x every 3 years. So to handle this, we have to take advantage of something called locality in the programs or algorithms. And locality is this property of algorithms. There are 2 main kinds of it, spatial and temporal. So spatial locality is how many accesses algorithms make to nearby data over a short period of time. And that makes use, so in the memory hierarchy, when you access 1 byte, you don't actually get 1 byte, you get 64 of them usually. So if you can make use of all the 64 that you get, that is better because you don't have to keep asking for data, which incurs latency cost. And that is called spatial locality, if you are able to make use of the data that you have transferred, the multiple elements that you've transferred at a time. Second kind is temporal locality, which is how many times you repeat accesses to the same data over time. And that makes use of the memory hierarchy. So there's these 2 factors. One is that memory moves in bundles through the hierarchy, and also that there are different levels. So like when you get a machine, they'll tell you like, oh, the L1 size is this much, the L2 size is this much, the DRAM size is that much. And it is faster to access the L1 compared to the DRAM, but the L1 is also much slower. So if you can access repeatedly the stuff that is in the L1, it's much faster than if you have to go fetch stuff from DRAM. So that's the memory hierarchy, and you can take advantage of locality in the memory hierarchy to speed up the average case to handle latency. So this is just some examples. L1, L2, last level cache. So L1 is like on the order of 32 kilobytes here. L2 is like 256 kilobytes. Last level is on the order of megabytes, and main memory these days is on the order of gigabytes. You can even get one like terabytes nowadays, which is pretty big. But the latency gets slower and slower as you go down. So like the average latency for L1 is like 2 nanoseconds, but in main memory it's like 50. So if you can access stuff in here, that is way better. Questions? Okay, so talk about the basics about how caches work. So caches are fast and expensive memory that keeps a copy of the data. So this is not something that you have to manage from a software perspective, though there is some kind of like software technique, like you can cache stuff in your program sometimes, like if you have pre-computed an answer, you can do like memoization, but hardware caches are not managed by the program and stuff like what is in, for example, like what is in the L1 at any given point or what is in the L2, that's not something that you have to manage in your program. But it is something that you can exploit in your program through exploiting locality. And so there's this cache, and the cache is made up of lines. So the lines are often 64 bytes long, and that's the number of bytes that are loaded together in one entry. So if you access one byte on one of the cache lines, the hardware will bring in 64 bytes around that data into the cache in one line. And it's like fixed size 64. It's not like if you access a byte in the middle of it, you will get the next 64. It's like you'll get the 32 before and the 32 after, because memory is cut up upfront into these 64 byte chunks. So this is an example. On the left side, we have some memory. On the right side, we have a cache. And the cache is much smaller than the memory. So not everything can fit in here, but there is some mapping between the addresses in the memory and the addresses in the cache. And yeah, so here, like this stuff, here it's mapped by the lower bytes, or sorry, by the lower bits in the address. So like 0001, 1011, and so like the lower bits of this are 00, and the lower bits of this are 10, even though like this one is actually lower in the total memory. But it doesn't really matter. Just here it's indexed by the lower bits. And the processor is here. So that's like, you know, the ALU registers and things like that. And the way this works is that if the processor asks for some data, first it will check the cache to see if that data is there. And then if it's not there, then it will go to the memory and fetch it into the cache. And if it looks for something and it finds it in the cache, it's called a hit. And if it misses it, or if it looks in the cache and it's not there, it's called a miss. And a cache hit is cheap because we have access to something in the cache, which has much lower latency. And a miss is much more expensive because then we have to look in lower, slower levels of memory. So there are a few ways that you can do indexing in a cache. The most straightforward one is called direct map. And in that one, it's basically how we did it in the previous example, which is that you use the lower bits in the memory address to determine the index in the cache. So the cache has some fewer lines than the total address space. And the way that you determine which location that an address should be in the cache is that you just truncate the lower bits, and that gives you some position here. And that is called a set. So here, the block size or the line block size is B. So you just ignore, so the addresses are going up by 4 each time. So like here, 0, 4, 8, and so on. So the offset, the lower log B bits are just, they're not factored into the address because you're just skipping over them. And then the set is determined by the middle log M over B, where M is the size of the cache and B is the cache line size. So M is the size of the cache in bytes, and B is the block size in bytes. So M over B is the number of cache lines you have. So log M over B is just how many addresses of these lines that we could have. And then the rest of it is the address space minus. So W is the total number of bits in an address, and the rest of it is just W minus log M, because these two sum up to log M. And in direct map cache, it is really easy to find a block because let's say that we look for an address. We look at the address, we know exactly which line it would be in the cache if it were to be there, and then we check if it's there, and if it's not, then we have to go to the memory, and if it is, then we're done. And on the very other extreme, so direct map is easy to implement from the hardware perspective, because like every location in the memory can only map to one possible address, or every location in the memory can only map to one possible location in the cache. But it's also kind of not good from a performance perspective, because if two lines, like here, these two red lines would map to the same location in the cache, And so both of them could not reside in the cache, but maybe in your program, you may be interested in having both of them. Like if these were submatrices, for example, in a matrix multiplication. And another thing to notice about direct map is that you may have eviction or like, so you can only hold one cache line at a time in each of these sets. And so if I wanted to hold these two red lines, one of them would have to be kicked out to make room for the second one, even though maybe like the rest of it is totally empty. And so like I'm just wasting the rest of the space, but it doesn't matter because there's only one location that both of them could go. So this is like the easiest to implement from a hardware perspective, but it's also the least flexible. On the other extreme, this is not something that anybody actually implements, but it is nice to think about, which is called fully associative. And fully associative means that any line or any address in your memory can go to anywhere in your cache. And so that would make full use of your cache because like if there was just any free space, then it could go there. Whereas in contrast, in direct map, if there's no space in the particular slot it's supposed to go in, then it has to be evicted. However, this is a bit hard to manage from a hardware perspective because if you wanted to search for something in the cache, you have to look through the entire thing. And the way to manage this is called a replacement policy, which determines if this cache becomes full, which line should you evict? Evict means just like you have to toss something out if you're out of space. And in reality, what we actually have in caches is called set associative, which is somewhere between direct map and fully associative. And that means set associative is kind of like, if you imagine direct map as like one long column, set associative is just kind of like if you had copied that column several ways, like you just copy and paste it horizontally a couple of times. I don't know, like, and those are called ways. So you may have like a 4-way associative cache or 8-way associative cache. And that just means like you copied that thing 4 or 8 ways horizontally. And so like in this example, it's 2 ways, but in reality, often it's like 8 ways. Yeah, and this example just means that like for every set, there are 2 possible slots for it. So then you could hold 2 red lines in this cache. So it's between direct map, in which there's only one location that something can be, and fully associative, in which there's M over B locations that something can be. Here there are K locations where something could be in the cache. All right, so there are 3 kinds of cache misses that we can incur. Well, there's actually 4, but the first 3 kinds of cache misses that you can incur are, you can think of them, you can remember them easily because they all start with C. The first kind is cold miss, which is the first time that a cache block is accessed. You have to incur miss because the beginning of time, everything is in the memory and nothing is in the cache. So the first time you read something or write something, it has to be brought into the cache, and that's a cold miss. The next kind is called capacity miss, which is that the cache copy of that thing would have been evicted even with the fully associative cache. So if that means that the cache just ran out of space and there's not much you can really do about it. However, in reality, we don't have fully associative caches. So we have things called conflict misses, which are the set is full, even though there may still be space in the total cache. There's no more space in this particular slots that it can go. So the block would not have been evicted if you had full associativity, but it will have been evicted with set associativity or direct map. When you introduce parallelism, you get other kinds of misses, which are called sharing miss. It's a bit complicated. So in shared memory, when you have different processors, there's something called cache coherence, which is if you have different processors and each one has a cache, you somehow need to manage, like if one processor updates the copy of the data in its cache, and that copy and that data resides in other caches, the changes need to be propagated throughout the other processors because everybody needs to read a valid view of the data. And so then it needs to be evicted in all the other caches to update the view of the data. And that's called a sharing miss. And there's 2 kinds of sharing misses. The first one is called true sharing, and the second one is called false sharing. So true sharing means that two processors are trying to update the actual same item of data, like the same element. And so that view needs to be updated in the processes. And false sharing means two processes are updating different elements in the same cache line. And so remember the minimum granularity in the memory hierarchy of the cache line. And so like if P2 updated this part, P1 would need to refresh the entire cache line. True sharing, there's not a ton you can do to avoid that if you need it, but false sharing, you can avoid it by padding at the granularity of cache lines. So one low budget trick is like if you're trying to compute a sum, for example, and one easy way to compute the sum in shared memory is like if you have p threads, you make an array of size p, and every thread accumulates into some entry of that array. But however, like then you would be subject to false sharing because two processes may try to update partial sums next to each other. And so you can pad them, each of them to be 64 bytes. Even though you might actually need like 4 or 8. But you pay a little bit in space and you can avoid false sharing. Okay. Yeah, so we had these three kinds of misses for the serial case. So we had cold, capacity, and conflict. And conflict misses can be a problem. Like this is just some example. So let's say that we're trying to access this submatrix A in this larger matrix, which is something that we would need to do in like matrix multiplication. And if we have set associativity, either set or direct mapped, then we may fall into this very unlucky case where, for example, like let's say we're trying to access this red column. And depending on how wide this is, each of these, if we're extremely unlucky, may fall into the same set. And so like we would want to hold all of these together in the cache, and maybe the cache is big enough to hold all of this entire column, but the set is not big enough to hold the entire column. And so then we would incur unnecessary conflict misses. And the way that we can avoid that is that we can copy into a temporary matrix, or we can pad the rows. Questions? So I have about 10 minutes left. And in the last 10 minutes, we can get into a little bit about how you do the theoretical analysis of these kinds of problems. And to do that, we're going to introduce this ideal cache model. So in the ideal cache model, it models two levels of memory hierarchy. We have a cache of size m bytes, and we have a cache line length of b bytes. And we assume that the cache is fully associative, and we have some optimal replacement policy. Obviously, these two last things are not fully realistic, but there's some theory that tells us that it can approximate something realistic, which we will have in a minute. And so, yeah, so there's m bytes in the cache. There's b bytes in a line. So we have m over b cache lines. B is like the horizontal length, m over b is the vertical length. And the memory is some unbounded size in theory. And so now we have these two performance measures. One is the work. So that's the normal running time that you would have in serial algorithms. And the second new one is the cache misses Q. And cache misses are measured in the number of cache lines that need to be transferred between cache and memory. So this is maybe a bit hard to understand at first. We'll see several examples, but in the cache misses queue, if something is using the cache efficiently, often you will see parameters like m and b showing up in the runtime or showing up in the cache misses. And in the ideal cache model, one cache line transfer is a unit of work. So it costs order 1 to transfer b bytes. Yeah, so this ideal cache model obviously is a little bit unrealistic. Like we don't actually have fully associated caches, and we don't have an optimal replacement policy because we get requests as they come in reality, like you don't know the entire future. However, there's some really nice theory back in 85 from Slater and Tarjan that tells us that if you have an algorithm that takes Q cache misses on an ideal cache of size M, then with a fully associative cache of size 2M that uses this least recently used replacement policy, which is not something that requires knowledge of the feature, it incurs at least 2 Q cache misses. So just to say it again, if you have a cache of size M and you have some optimal replacement policy that knows the feature, and that will take Q misses, then with twice the space in your cache and a worse replacement policy, you can get within a constant factor, which is 2 of the cache misses. So this is like, I mean, back then, the proof is actually not super complicated, but it's really pretty because like, this is the first time that they introduced some idea called like resource augmentation, which in theory, for people that are really interested in theory, resource augmentation is like you give the online algorithm, which is the algorithm that doesn't have knowledge of the future, more power in some way. Like here it's size, but in other settings it might be like time or space or something. And this is kind of like the first place that it actually appears. So in theory history. Anyway, so for asymptotics, you can assume what this means for ideal caches is for asymptotic analysis, because these constant factors go away in big O or big theta. You can assume either optimal or LRU replacement, which is a more practical online algorithm, as convenient. So that's why we can prove things in the ideal cache model. From an engineering perspective, these are the steps that you can use. You can design something that is theoretically good in these models. You probably have to do some more low-level performance engineering for better performance, because real caches are not actually fully associative. So you may need to deal with like the set associative padding that we were talking about earlier. And also in reality, like in this model, we count any cache line transfer as cost 1. There's several unrealistic things in this model. One is that we are only counting cache line transfers, but obviously, like depending on what you do on the cache line, it may take more time to do more work on that cache line. And also in reality, loads and stores have different costs with respect to bandwidth and latency. So you may want to try to reduce the number of loads, or sorry, the number of writes or stores, because those are more expensive. But this is like a good first pass to do the analysis, because you kind of have to lose something when you do theoretical analysis. Like there's some cost of abstraction, but it's a good first shot. So this is an example of how you use this model. Suppose that you have a program that is going to read a set of R segments, where the ith segment has some S sub I bytes. And suppose that if you add them all up, that is n bytes. Why can't real caches be fully associative? It is hard for the hardware to manage, because hardware is like, ideally hardware has minimal overhead because you want to reduce the margins. And so like for fully associative cache, you have to search the entire cache to find a cache line. And that would be expensive and has some cost. So that's why in reality, we have set associative, which is like, it has some of the benefit, but yeah, it has some of the benefits because like it's not direct map, so there can be multiple ways, then multiple slots, but it is too expensive to read the entire cache to find a single thing. Thanks. Okay. So yeah, so suppose that we're trying to read these segments and they all add up to n bytes, and this n bytes is less than m over 3. M is the number of bytes in the cache. And n over r, so the average size of the data segments is at least b, which is the number of bytes in a cache line. Then we can prove that all the segments will fit into the cache, and the number of misses to read them all is at most 3n over b. So remember, in this model, the metric q, which is the cache misses, we're only counting the number of transfers. We're not counting like any additional computation that happens on those lines after you bring it into the processor or into the cache. And yeah, so the proof is like this. Suppose that you read these R data segments, and reading a single segment incurs approximately S sub I over B misses, assuming that these segments are contiguous. And actually reading S sub I bytes will take at most S sub I over B plus 2. Like if you look at this picture, this is your segment S sub I, and it can roll over a little bit, at most 1 on the left and at most 1 on the right. So that's where this plus 2 is coming from. and the rest, this part is bounded above by S sub I over B. And that is N over B plus 2R, because we know that the sum, if you sum up all this S sub I, that's just N. So we define it up there. And then if you do a little bit of algebra, then we will get bounded above by 3N over B. So yeah, so this is the way to think about how to analyze things in this model. We're only counting the cache line transfers, and this is pretty exact. In reality, like we're gonna prove things in theta notation, but it's like how to analyze it. You're counting the number of blocks that something is taking up, and here it's just, but you have to round up to the next nearest block because the minimum granularity is a cache line. So that's why there's like one extra on each side. In the ideal cache model, we also have some assumption about how tall a cache is, which is that the block size squared, which is at the memory, or sorry, which is at the cache size, is at least the cache line size squared for some sufficiently small constant. And this is one example about why it's a realistic assumption. So the cache line length is 64 bytes, and the cache size is 32 kilobytes for L1. That is more than 64 squared. And the reason that we want to make that assumption is because one thing that we often analyze in this model is matrix algorithms. And for matrix algorithms, usually to be cache friendly, you kind of like cut the problem up into subblocks and or into submatrices, like usually square submatrices. And so if you don't have a tall cache, the entire square will not necessarily fit in the cache vertically. Like if you have B, if your side length is B, then it also needs to be B vertically. Yeah, but if you have a tall cache satisfying this constraint that the cache size is at least the cache line squared, is at least the cache line size squared, so B squared. And suppose that, so you're trying to read this n by n submatrix, which has n squared elements, and suppose that this n squared elements is bounded between, is less than m over 3, which is like the memory by the cache size over 3, then A, this entire submatrix, will fit into the cache using the thing about the segments that we just showed. And the number of misses that we have to incur to read them is at most theta n squared over B. This is like something, this is like a lot of machinery to prove something that's pretty natural, which is like if you're trying to read a submatrix of size n squared that has fewer elements than your cache size, then it will take the number of cache lines over B, or sorry, the number of elements over B to read them. Yeah, I think that's a good stopping point because we're almost at time. So I'm happy to take any questions.